We have obtained the solution. We have seen how this solution for the simple harmonic motion, this formula for x in terms of t, can be derived by thinking about the motion of a ball in a circle and comparing it with the up-down motion in a spring. What I'm going to do next is to make use of the follow-up on this idea about the circular motion and derive one or two other useful formulae for simple harmonic motion. Let me clear this up first. Now, I would like to derive expressions for, let's see, I would like to derive expressions for the velocity and for the amplitude. So let's see how that is. Now we have seen that this is x is given by this formula. So now let's think about the velocity. I'm just going to draw a line from the origin to the ball. So that length is the radius. Now I'm going to think about the velocity now. The velocity of this ball, okay. Now I'm going to call this the speed of this circular motion v c. Okay, to distinguish it from the velocity of the simple harmonic motion. So as we have seen, the height, I can choose this circular motion, okay, so that the height of this ball always follows exactly the height of this ball in the spring as it goes up and down. So they're always at the same level. Okay, so what I want to do now is I want to find an expression for the velocity of this ball in simple harmonic motion. I want to find that. So this x value, the x value of the x displacement of the ball in the spring is just this value here. So if I want to find the velocity of this ball in the x direction, that is just the vertical components of its velocity. So in other words, I just need to find the vertical components of this vector. Now, how would I do that? Okay. So let me start by looking at this angle. Now we have seen that this angle theta is actually the same as the omega t. That's actually theta. Okay, and which is why x is given by this formula, where a we now understand to be the radius of the circle, which is the same as that line, the radius. So therefore x, the value of x, which is this value, is simply a times the sine of theta. Now, if I look at vc, this velocity vector is at right angles to the radius. It's at right angles to the radius. So this means that let's see how we can draw this. This means that, for example, if I imagine moving this vector, moving this vector to here, alright, just shift it down like an arrow, but keeping the direction fixed. Okay, let's say V shifts down to there. So this is my VC here now. Then to find the vertical component, of this, now notice that is a right angle, because this is a right angle. So this is also a right angle since those two lines are in the same direction. Therefore, since this angle is theta, this angle must be theta. Okay, so in order to find the vertical components of VC, all I need is to take VC times cosine theta. So that should give me the vertical velocity of this motion in the spring. So I can write that down now. V, the vertical component, is equal to VC, times cosine theta. Now, but I like to express this in terms of time, and express the VC in terms of the amplitude. So how would I do that? So recall that VC, the velocity, is related to the angular velocity by omega times the radius. Angular velocity times the radius of the circle. Now in this case, the radius of the circle is A. Okay, so it's omega is really equal to omega A. So therefore VC is omega A. And theta, we already know, is omega t. So there, we have just derived the formula for velocity that we have seen in earlier sessions. That's the velocity. I'll just complete the picture by writing out the expression for the acceleration in terms of sine or cosine, which is pretty straightforward because we already know this formula. So I'm just going to write this out. So A is equal to minus omega squared, and X is equal to A sine omega t. Just substitute this into the X there, and I get A sine omega t. So now I have all three of X, V, and A in terms of sines and cosines. Now, while we are here, there's something I should point out. Alright, something I should point out, which is that this formula, X equals to A sine omega t, it obeys this equation. Okay, it can describe this simple harmonic motion. But it is important to know that this is not the only formula that works. There are other formulas that works. Now, to understand what I'm talking about, go back to the circle. All right, go back to the circle. Now, remember how we described the motion of the ball starting from t equals to 0. When t is equal to 0, I've described the motion of the ball as starting from x equal to 0. Right? This agrees with this formula that when t is 0, sine of 0 is 0. Okay, so this formula describes a motion that starts at zero displacement when time is 0. So it goes up and down. But the time equal to 0 is just where we choose to start timing the observation, if you like. So I can choose to start timing the observation at a point where the displacement is not 0. Why can't I do that? And if I choose to time at any other timing, the starting displacement might not be 0, but the subsequent displacement will still be the same kind of up-down simple harmonic motion. So why should I be restricted to just starting to time when x is 0? Well, the answer is quite simple. I don't have to be restricted. So, but what if then if when time t is 0 and x is not 0, then surely this formula is not going to work. Okay, because in this formula, when t is 0, sine 0 has to be 0. So what's going on? Right? Is there something incomplete or wrong with this formula? Well, to understand what's going on, or how we can use this formula more think of it in a better way, let's go back to this circular motion. Remember, when I say that I start timing this motion, I start at t equal to 0 when x is equal to 0. In the circular motion case, this is when x starts from this position, when x starts here. So x starts here when t is equal to 0, and then it starts going round and round. So the case when if t is equal to 0, x is actually not 0, corresponds to the case when x does not start from here when time is 0. For example, x can start from there, right? What if I start timing here? So x is at a non-zero value. Okay, and how would the formula change? Right, the way it would change is simply this. I would have to add a number to the time. Okay, so for example, if I start timing here, let's say t is equal to 0 there, what would that formula look like? So if the time t is equal to 0 here, and I start with a non-zero x, so maybe when time t is equal to 0, the theta here is maybe theta 1, for example. So therefore, in the beginning, when t is equal to 0, this argument here for the sine has to be theta 1 instead of 0 when t is 0. So I can modify this quite simply by adding a theta 1 here. So you see, when t is 0, I have sine theta 1, which agrees with this angle. Okay, so this would actually be a more general form, right? Form of the solution of the x formula that I can actually use even when I don't start timing here. Okay, so in a way, you can think of this as a more useful form. And then, of course, I can also have, instead of sine, I can also have cosine, and that just means that I start from there instead.